Alrighty, let's see what we got today. Hard. Okay. Um. So count the number of arrays with k matching adjacent elements. You're given integers n, m, and k. A good array of size n is defined as follows. Each element in array is inclusive. Each element in array is in the inclusive range of 1 to m. Okay. Exactly k indices where I1 is less than or equal to I less than n satisfy the condition. Array at I minus 1 is equal to array I. So consecutive elements are the same within the n size array. Return the number of good arrays that can be formed. The number of good arrays that can be formed. And then since your answer can be large, use modulo 10 to the 9th plus 7. So n is equal to 3, m is equal to 2, k is equal to 1. Each element has to be 1 through m. And there's going to be 4. So here, so how many ways can you do a 3-sized array where the numbers are 1 through 2, so 1 or 2, and the number of indices, or the number of consecutive number of pairs of adjacent indices that are the same as 1. There's 4 ways of doing that. 1, 1, 2, 2, 1, 1, 2, 2, 1, and 1, 2, 2. Okay. And here n is 4, m is 2, k is 2. So the numbers are 1 through 4. You have to have 2 pairs of consecutive values that are the same. They can be overlapping. And then m is 2 means that the numbers are 1 and 2. So like I'm guessing 1, 1 has to be exactly k indices. So 1, 1, 1, 2. Yeah, 1, 1, 1, 2 is 1, 1 and 1, 1 are matching. 1, 1, 2, 2, 1, 2, 2, 2, 2, 1, 1, 2, 2, 1, 1, 2, 2, 2, 2, 1. Okay. Interesting. And k equals 0 means that they all have to be, they can't have the same thing. Okay, so let's go ahead and start by creating the mod constant. Alright, so let's consider the k equals 0 case where you have non-matching. You have everything being different. If everything is different, then actually let's look at the constraints here. So n is a pretty big number, m is a pretty big number, k could be the maximum possible. Like if you have 10 elements, then the maximum number of consecutive pairs that are the same is 9. Like if you have all the same number, there are going to be 9 consecutive pairs. Okay, so interesting. How would I do this if there was no pairs that are the same? Then I think it would be like m times m minus 1 to the power of n minus 1. So if it was like k equals 0, and let's say n is 5, and m is 4. So there's basically, if you use counting principle, the number of ways of doing the first thing is there's 4 possibilities there, and then 3 possibilities on the second one that doesn't match the first one, and then 3 possibilities on the third one that doesn't match the second one, and 3 possibilities on the fourth one that doesn't match the third one, and then 3 possibilities. And they're kind of, so this is like 3 to the third is 81, 81 times 4 is, or 3 to the fourth is 81, 81 times 4 is 3 to 4, 81 times 4, 3 to 4, which is equivalent to, I think, m times m minus 1 to the power of n minus 1. Alright, so let's go ahead and try that. So let's say if k equals 0, then return m times n minus 1 to the power of n minus 1. Okay, and then test case here. Let's say this is 5, 4, 0. Okay, 324. Okay, so I have a grasp of the k equals 0 case, but that is far away from the k equals whatever case. So let's consider if it was k equals 1, maybe. K equals 1 and k equals 2. So if you have 1 out of the 5, then there's going to be if you have n elements in your array, there's going to be n minus 1 kind of consecutive pairings, consecutive adjacent spots. So if one of those adjacent spots is going to be used for something that's identical, and the spots that are surrounding it are all different. If the first spot is adjacent, it's the same. So that means that it would be something like 4 times 1. Here, let's say that's parameters, or the other parameters are the same. And then from there, it has to be all different, right? So it'd be like 3 times 3 times 3 times 3. So that's 4 times 27, which is 108. Doesn't matter if it's the first set of numbers or the first pair that's the same, or some other pair. If it's some other pair that's the same, let's say it's like the second and third elements, it'd be 4 times 1 here, and this thing would have to be 3 ways of doing this one that's different than the second element, and so it's the same. So let's say if k is 1, then this would be something like you have 1 less spot to choose from. So you have, so how many rearrangements this is going to be? The 4 and 1 can be in the first set, second set, third set, or fourth set. So there's like n minus 1 spots to maybe choose to couple it, times 4 times m as the number of the ways that you can put a number in that spot, times m minus 1, and the other spots you have m minus 1 ways of putting that, so that would be like 3, and then to the power of n minus 2. let's see if that works. N is equal to 5k. So this should be 108. Ooh, did I miscalculate this? So my formula worked, but oh yeah, it's a 108 for each iteration of this, but then there's like 4 different iterations, 4 different iterations, so it'd be 4 times 108, it's 432, okay. So that's fine. All right, moving on. K equals 2. We're going to hopefully do this until, or I'm going to do this until hopefully I can generalize to K equals whatever. So here, 2 path here is going to be, let's say it's the first 2 that's the same, and the second 2 that's, or first, like the first set and second elements are the same, and maybe the second and third elements are the same, or the third and fourth elements are the same, and maybe the last element's different. So I think that's the way that you multiply it. Like you have 4 options for the first one, it's the same for the second one, so there's only 1 option there. It has to be different for the third one, same for the fourth one, and has to be different for the fifth. So that's like 12 times 3, which is 36. How many ways can you rearrange that? So there's one thing that's different. So that means that that one thing that's different can be in any of the spots, but no, it can't be in the second spot. I guess the second spot would not fit. So it could be in the first spot, third spot, or last spot as the way to kind of divide where the pairings are. Pairings could be the first 2 elements, like 1 and 2, 3, 4, or it could be 1, 2, 4, 5. So I think there's 3 ways of doing this. 3 ways times 3 different permutations of this. As in, like, say you have pairing, and singleton. The singleton could be between the pairings. I'm saying pairing is the things that are consecutively the same. And then the other option for it to be 2 is if you have 3 in a row that's the same. So P, 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 and then 2 singletons. In that case, that would be 4 times 1 times 1 times 3 times 3. Times 1 times 1 times 3 times 3. Which is going to be also 36. Interesting. And the singletons and the 3 that are the same could be before or after or could be from the first, second, or third spot starting. So it could be this, or it could be that. So there's also another three ways of doing that. How to generalize this? So I say here, if this is equal to 2 is the number of pairings, I think would be something like n minus 1, which is the 4. No, that's m minus 1, which is the 4. No, that's 4's, no, 4's m, right? M, and you also have two n minus 1's. And you have n minus 1's as well. Because k is 2, this has to be the power of n minus power of n minus 3, I think. The reason why there's two of these is because if you take 5 and subtract 2, you're left with 3. So it's going to be n minus 3. Is that right? The reason why there's, so if this was more n, it would, yeah, you're taking up 3. You're taking up 3 spots for the 1 and the 4 and the 4. The 4, 1, 1, that's 3 spots. You're taking up those 3, and the remaining spots are going to be all different. So it's going to be n minus 1. Yeah, I think this is, and okay, so that's the count of 36. And the reason why there's 3 different permutations. Do I want to generalize this into one kind of generic thing, and I say there's 6 permutations of this overall? Or do I want to try to separate this because it's somehow different, that somehow coincidentally came out to be the same with this permutation of, or these set of parameters? I'm going to say it's probably going to be the same, but just 6 permutations. So 4 times 1 times 1 times 3 times 3, that's the same thing as all this. How do I know that there's 6 permutations? Because there's going to be, how many ways can I get it to be 3 consecutive, plus how many ways can I get to be two different pairs? Now are those always going to be the same? One thing I should probably do is test to see for other test cases, for other parameters, that the k equals 0 and k equals 1 is always true. So let's say for a random test case where, let's say you have n can be pretty big, right? So 200, m is, let's say, 40, k is 1. Oh shoot, I need to make this within modulo. That's too big. Oh. What's going on here? Somehow I changed daily questions. Okay, so %mod. Yeah, %mod. I think I might need to do modulo with the powers. Okay, so yeah, this is correct for a big case of n equals 1. And then for big case of n, or k equals 1, big case of k equals 0, okay, that's still fine. What was it? Python mod exponential or mod pal was the pal function pal base exponent modulus. Okay, so I think this should probably be using that. So it'd be like pal bases n minus 1 powers n minus 1 using mod. This is pal bases n minus 1 powers n minus 2 mod. There's the mod. Do I have an extra parentheses here? Seems fine. Okay. It might be, that probably is faster than doing a huge power without it. Alright, so what do we do here? So if you have two separate pairs, then the number of spots, the number of places that you would be able to choose that would be if you have two separate pairs, the number of places that you would be able to choose that is or choose one. No, it'd be 3. How do I think about this? Two separate pairs. Well, you cannot choose. Okay, so let's say you had like 10 spots, right? So you had 10 spots. I guess it probably makes more sense to label it like this. So you had 10 spots for your array, and you had two pairs within that. And then there are nine kind of connections where the pairs can occur. And any of those connections could work. So there's 9 possible connections. In this case, that would equate to, since n is 5, that would equate to 4 possible connections. That would equate to 4 possible connections. Is that how I want to try to count that? How did I get 3 out of 4? You have 2 pairs. You have 1 left over. 1 left over comes after or between the 2 pairs. I see. So if you had 2 pairs and there's 8 left over, then how do you put the 8 around the 2 pairs? Well, no, so if you have 2 pairs and there's 10, then there's 6 left over. How do you put the 6 around the 2 pairs? Is that really how I want to try to count that? We have 10. Pick where the first pair is. That leaves you with 8 spots. Does that leave with the 8 spots? Not really, because if the pair was put on the second and third elements, then you can't really put a pair in the first spot anymore. If you start with 2 pairs, how do you put 8 or 6 things around it to make 10? So 6 things could be all before it. 6 things could be 5 before, 1 middle, 0 at the end, or 5, 0, 1. Which is more like your so what do I want to think about? Maybe I want to think of the pairings as one group, as one element, consecutively the same. So it's more like thinking of it as like CCS, consecutive the same. Or I guess maybe pair, singleton, singleton's pair. So if I had 10, of which 6 of them are pairs, or 4 of them are paired, 4 of them are elements of pairs, then it would be 6 and then 2 p's. Yeah, okay. Or it could be 5 of them, 2 p's. So I'm doing 8. I'd be doing 8, choose 2 for where the pairs are. Here I'm choosing this 3, choose 2, or 3, choose 1 as where the pairs are. So the number to choose from is the number of pairs plus the number of singletons. So 3 permutations, because there are 3 groups: pair group, pair, another pair, and a singleton group. And 3 groups, and 3 ways of permuting those. And I guess this one is actually, you have a triplet. I guess this is more like a triplet that's the same rate. If I were to try to separate pairing versus so here it's triples, triple, singleton, 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 triple, singleton, or singleton, singleton, triplet. Okay. Okay. So how to generalize that? If I were to the number of ways. So it's either 2 pairs in a singleton or a triplet and 2 singletons. So it would be the number of things would be n, what's it, combinations of, is it Python combinations? Gosh. So nr math.com. Okay. Math.combinations. So it should be the number of pairings plus the number of singletons, where each pairing removes a singleton from n. So I think it should be n minus k. K here is 2. So there's 3. And then you're choosing how many ways, so it's choosing k ways of orienting that. Okay. Yeah. And that's for pairs plus singletons. Separate pairs, 2 pairs plus singleton. If I did triplet and 2 singletons, the triplet would be math.combinations n minus, well, here I guess k is just 2. I know k is 2, so I can say this is 2. And triplet would mean that there are n minus 3. N minus 2 and n minus 3 is going to be the same. No. N minus 2 triplet, singleton, singleton. How would this end up being the same? So this is n minus 2 is the number of groups. Is it still the same number of groups here? How is it still the same number of groups? If this was a triplet in the tens case, then there'd be 7. No, there'd be 7 singletons in a triplet. So 1, 2, 3, 4. This is 8. So it ends up being the same. 7 singletons in a triplet versus 6 singletons in two pairs. Huh. Okay. So I guess it's still n minus 2. But I'm choosing 1 in this case. Oh, whoops, I didn't have a test case for this. Okay, so test case, say 2, actually, let's use the 542, and I'll just pause in this test case. Okay, so it worked there, 216, which is 36 times 3 times 2. Okay, so then for the more general case, or the bigger test case, I guess. Oh, whoops, I forgot the mod. Okay. wonder if I actually do need to wrap all these things around mod, or if I can do some multiplication of this thing with mod at the end. Okay, so it worked for the generator. Okay. So k equals 2 is solved. Alright, see if I can generalize here. 0, 1, 2, Cancun. Okay. Say k is general. How to work with that? What pattern do I see here? It looks to be, I guess I can try to generalize based on the formula before here. Oh god. So you have some power m minus 1. Yeah, so this thing's the same right here, right? This is pow of m minus 1 is the base. N minus 3 is the thing. Is the exponent mod. And I guess that covers your singletons, right? That covers your singletons. Because every time you have a singleton within the array, it's going to have n minus 1 or m minus 1 possibilities there, and you're going to have n minus 3 of those all the time. Really? I guess. No, that's not true. How did this work out? Guess you don't have. Guess I'm. So the singletons are the 3's here, but these 3's are not both singletons, actually. Like this 3 is something that's different than this 3 is a singleton by itself. If these are meant to be pairs, this 3 is just meant to be something that's different than the other thing. So I guess I shouldn't say this is number of singletons. This is number of things that are different than the previous thing. Okay. And because there's two pairs or two things that are consecutive that's the same, the things that are not consecutive that are different must be n minus 3 of those things. Or there must be n minus 3 things where they're different from the previous things. You start off with 1, always, that's like any possible thing. And then the things that are after it there needs to be some number of them that's different than the previous one. And I guess that's n minus 3. So kind of doing a blind test here. If k equals 3, then I'm going to have something with the mod. It'll be m times power m minus 1 n minus k plus 1 n minus k minus 1 taken to the power of mod, or taken to the power of taken with the mod remainder. And then I think this is probably going to be a full loop. I think the remaining terms is probably going to be some combination, summation. Or this thing could be, this is the start, So the value is equal to m times power of, this is the baseline calculation, and then there's going to be some loop that iterates over it. I guess iterating is going to multiply this thing by some other thing. So how's the combination going to work? So if I have three pairs, okay, maybe I need one more step. If I have three pairs and there's five, well, I can't even use five anymore. Let's say there's n is 6 and m is still 4. So that means there's three pairs. So it's like P, 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 and P, P. That's 4 times 3 times 3. Or it could be P, no, that's the only way that works out, right? It could be a triple, so it could be triple, 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 and then 3 singletons. Or it could be singleton, triples, 2 singletons, singletons, triples, and then singletons, and then a triple. Each of those should be 4. Ooh, that's not the same actually, huh? That's 4 times 3 times 3 times 3 times 3. Eeks! Is there any other ways that I can get, let's see, there's actually pair and then a triple representing 2 pairs, or being the same as 2 pairs. And obviously that could be reversed. And then, so this is, and then there's like different ways of orienting that. So there's basically 3 things here. There's a pair, a triple, and a singleton. And then I can do that. Obviously, okay, yeah. So if it's 3 pairs, basically it's like PPP, and there's only there's only one orientation of that. Is this supposed to be using iterative approach? Should I be using like recursion or a stack to do this? I guess maybe I could. Maybe I could use a stack to do more recursion for this. Okay, so pair, 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 and a triple. I think that's the only, and then triples. Actually, this is not even going to work right. This is actually supposed to be, well, let's see, the count for this one was going to be 4 times 3 times 3. Okay, so this is actually 4 times 3 times 3. I think I screwed this up. I think this should have been, it's not a triple. It actually seems to be like a quadruple. Yeah. Because it's k is 3, then it needs to be 4 things in the thing. 4 things in the sequence in order to make it have 3 pairs, 3 consecutive things that are same. Okay, so there we go. So it's still the same as 4 times 3 times 3, which is still this value. M is 4, n minus 1 is 3. Yeah. Huh. Okay, so the base is still the same. This is similar to saying that, yeah, this is like you're choosing like 3 choose 3 here. You're doing is this 3 choose 3? Yeah, 3 choose 3. This is how would I generalize this? What? PTS? 3 objects, and three different objects, 3 ways, or 3 spots. 3. And this is 3 choose 2. 3 choose 1, where the 1 is for the Q, the quadruple. What's going on here? Math combination. N minus 2 choose 2, n minus 2 choose 1. This is out of number of pairings is what? So they can be all separate pairings. So K is representing the number of distinct pairs, which was this thing. If you don't have K separate pairings, so let's say you don't have 3 separate pairings, but for each pairing that you remove, you're getting like a longer chain, like 2 pairs becomes a triple, or 2 pairs becomes a triple, or 3 pairs becomes a quadruple. Right. 2 pairs becomes a triple, 2 pairs becomes a quadruple. And then what? So if you had 3 pairs becomes a triple, the number of singletons increased by 1. And if you had So if you add an extra pair, if you add an extra p to a pair, that creates another singleton somewhere along the chain. I guess how many ways can you do that? So this is, you have 0 singletons. Yeah, this one you have 0 singletons. This one you have 1 singleton. The number of elements is always the same, right? The number of elements is always the same. So if say I expanded this out, let's say n is 10 here, then I would have 4 singletons. So it'd be n minus k. This is the combination of n choose r, where n is n minus k, or be 7 choose 3 or 7 choose 4, however you want to think about it. 7 things choose 3 for your p, or 7 things choose 4 for your s's. And here again, if I expand this out to be 10 rather than just 5, this would be 3 more s's. 2, 3, 4, 5. No, 5 more s's. And this would be like, well, this is not going to be straightforward. This would be like 7 choose 1 for where your pair is, times what's the easier way there? It's like 7 choose 2 for 7 choose 5 where your singletons are, times 2 choose 1 for where your remaining p is, and then like 1 choose 1 for where your remaining triple is. And then here it'd be k is 3, n is 10. This would be equivalent to, the number of ways of doing this would be 7 choose, oh, this would extend out to be 6 more. Seven choose 6, or 7 choose 1 for where your q is. Interesting. This one is the tricky one. But I think this is correct. You have a for loop that iterates through every possible sub-combination. And it's addition on those. Yeah, it's the permutation of that. So sub-combinations start with 0, and for k from for, let's say, I in the range of k. This one's straightforward because it's all like this one's straightforward because basically the type of things that are not singletons is the same. It's all pairs. This one's complicated because it's pairs and triples. This one's not complicated because it's just singletons and a quadruple. Interesting. So if you go, it's like 0 pairs, or the most pairs, just 3 pairs, 2 pairs, or 2 pairs, 3 pairs, or 2 pairs and 3 pairs. Why can't you have 2 pairs? You replaced 2 pairs with a triple. So, okay. So it's like all pairs, which is 3 pairs. So you never go down 1 pair. I guess you can't really go down 1 pair. Like you can't go from 3 pairs to 2 pairs. Because what's going to happen with the other thing? There's going to be another pair if you go down to 2 pairs. So 3 pairs, 1 pair, 0 pair. If this was 4, k is 4, then you have 4 pairs. And then you go down to 2 pairs and a triple. Excuse me. Two pairs and a triple. Or you go down to 1 pair and a quadruple. Or you go down to like a quintuple. I'll just use F for 5. Or you go down, I guess here, instead of 2 pairs, it could be a triple as well. So it could be 1 pair, no, you replace 2 pairs with a triple. So triple, 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 triple. Is there any other variation there? Are these all, they're all going to calculate the same, huh? This all ends up being something like 4 times 3 times 3 times 3. Yeah, because there's some flavor of the pair, some flavor of the pair, some flavor of the triple, and some flavor of the singleton. Yeah. So they're all the same in terms of the individual calculation of how many ways of doing that one type of thing. Then the question is how many ways of varying that type of thing. easy way of doing this. So I can change 2 pairs for 1 triple. I can exchange, so let's see. So P, so I can say anytime I see 2 P's, I can make that triple. Anytime I see a triple and a P, I can make that into a quadruple, and a quadruple and a P, I can make that into like a fiver. Technically, this is going to be like that. Something like that. Two pairs can become a triple and a singleton. Feels like a dynamic programming approach would be appropriate here. Just feels like that, unless there's a more direct approach. So replacement. So you start off with all pairs, and then you can do any sort of replacement calculation on those. Interesting. But the replacement. Orientation matter. So somewhere, so if you start off with 4 pairs, you can make it into 1 triple and a pair, or 1 triple and a singleton. And then you start off with a triple and a pair, then you make If I have an array of the number of pairs, triples, fives, singletons, that would be a for loop. I would probably need a for loop to calculate how many ways of doing that, right? Like some number of ways of choosing where to put the singletons, and some number of ways of putting where the pairs are, some number of ways of putting where the triple is. I guess I need probably a more generic way of doing this. Some generic way of doing this. I wonder. Are these all? Is this section of the? Could I section off the array in terms of spots where it's purely singletons versus spots where I'm doing this sort of calculation? So for instance, if I said that this was case 4 where n is, let's say, start 10, right? So if this is 4 and 10, then there'd be an additional 4 or 2 elements here. To make it 10 elements long. But if this was, let's say, 100, then there'd be just a bunch of S's. Like maybe 92 S's, singletons, in addition to the starting 8 here, could I maybe say that I'm going to choose out of the 100 8 spots where I'm doing this sort of calculation, and of these 8 spots, try to figure out how many ways of doing that. I think that's probably fine. I don't think there's any overlap there. I guess everything here I think is unique. Like these 8 spots determine the uniqueness of the whole thing. I don't think any of these 8 spots are redundant. So it could be something where it's like you start with the overall kind of shell of this is going to be, you have NCR where you're choosing out of your n spots in your array 2k spots where you're doing this manipulation, doing these exchanges of pairs with triples and triples with quadruples. And then it's a matter of how you want to do the 2k spots times some ways to have k consecutive k stuff in 2k in the 2k spots. Does that work? That might not work actually, because you can't really choose. Yeah, that can't work. I'm thinking right now of it being all. I'm thinking of this being all kind of grouped. But out of 100 things, if you choose 8, the 8 doesn't necessarily. The 8 things don't necessarily aren't consecutive, so it doesn't necessarily work. Actually, yeah, this is just right. So if it is 10, yeah, it's just not going to work. So every time you see 2 pairs, so the initial calculation is pretty straightforward. If you just have pairs and singletons, then it'd be, if it was just pairs and singletons, it'd be NCR n minus k, no, n minus 2k, no, n minus k minus 1. So this ends up being 4 and 2, so it's 6. So that's like, so 6 elements, and you're choosing 2 of them. So if it's all things, then it would be n minus k, choose k, or choose n minus k, choose k, or n minus k, choose n minus 2k. Yeah, I think that's right. So that's 10 minus 4 is 6, 6 choose 4, or 6 choose 2. N minus k, choose n minus 2k. Does that work for other things? Let's say if n is 100, let's say k equals 4, n equals 100. So that'd be n minus 4 is 96. Choosing 4 to be pairs, or 96, choosing n minus 2k, and choosing 92. Yeah, I guess k plus n minus 2k is equal overall to n minus k. But yeah, mathematically checks out. Okay, so that's the number of combinations for, this is ways if all pairs are kind of distinct, like there's no triples. And then you go into how many ways to produce triples from that. How many ways to produce triples from that? So for every 2 pairs, you can substitute it in a triple. And then for every 3 pairs, you can substitute in. Yeah, this feels so much like dynamic programming. Every 2 pairs, you can substitute triple. And then you have to recalculate it. So if you had an array where you said your number of pairs, maybe you even say your number of singletons. So let's say you had 4 singletons, 2 singletons, 4 pairs, and everything else is zeros, right? And then you could also have an array where it's 2, 2, 1, where you have two, so basically you have singletons, pairs, triples, quadruples, fives, and whatever. So you can also have, you can make the triple and a pair become a quadruple, so it could be 1 like that, or you can make the pair become 2 of the 2 pairs become triples, so 2, 1 here could become 0, 2. And then I guess that's it. The highest it can be is quadruple, right? Quadruple, and then 2 singletons. Or am I wrong with that? Yeah, it's quadruple. It's quadruple. Oh, I'm changing the singletons wrong. So I can change one pair to be triple and a singleton. Change the triple and triple and a pair becomes another singleton and a quadruple. Or I can change these 2 pairs from a triple and a singleton. So 2 triples. Wait, is that right? No, that's not right. So these 2 pairs becomes a triple and a singleton. Wait, 2 2 pairs becomes a pair. 2 pairs becomes a one single. Three. Let's add 10. 2 plus 3 is 5. 4 plus, no, that's what is going on here. So how can I not change these 2 pairs? Okay, actually that's right. So four singletons and 2 triples. 4, 6, 10. Okay. So I could individually calculate each of these arrays. The number of ways, like this ends up being 10 choose 2, or no, it's not 10 choose 2. There's 6 different things, right? So 6 choose 2, or 6 choose 4. This ends up being, I don't know, 6 choose 3 times 6 times 3 choose 2 times 2 choose 1. Choose 3, 3 choose, yeah. And this ends up being 6 choose 4, 4 choose 1. No, 2 choose 1. And then 1 choose 1. This one should be 1 choose 1. This is the same thing as the first. 6 choose 4. I guess maybe I don't need to include 1 choose 1. Oh, it's more complicated. 2, 4. 2, 4 becomes 2, 4 becomes 3, 2, 1, or it could become 4, 0, 2. It seems so slow. Seems so slow. Six choose 4, 2 choose 1, 1 choose 1. Do 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 do. I mean, even if I were able to come up with these arrays using some sort of for loop and a stack and some logic behind transitioning from one array to another array, it seems so slow to try to calculate all these things individually. There's going to be a lot of variations on these arrays. And then the calculation would be a for loop to iterate through all the elements that are non-zero. But maybe that's not too slow. Oh gosh. Oh my god, that's a huge number. 10 to the 5th. 10 to the 5th elements. Do I need to go back and try to figure out a better generalization of this shit? Ooh. What is a better generalization of this? That's not so granular. I mean, I think a single for loop, a single pass that does 10 to the 5th constant time calculation, so no inner for loop, would suffice. So it can't be n squared in terms of speed. Actually, I don't think this can be dynamic programming. K is just too large. Generally, dynamic programming is like nk. Or O nk. So it's probably linear. Like, I mean, it's probably linear. That's my guess. I mean, maybe it's still dynamic programming in a way that I'm normally not thinking about. So if I iterate, if I were to leverage, can I leverage like k equals 1 with k equals, or k equals n equals some number k equals 0? Can I leverage the k equals 0 answer and the k equals 1 answer? So a for loop that goes over k still. A for loop that still goes over k. So let's say n is equal to 100, k is equal to 5. If n is 100 and k is equal to 0, then you have 100 s's, and that ends up being like m times m minus 1 to the power of 99, or n minus 1. Then if I had k equals 1, k equals 1, then it's still, let's say this is your base. Is this your baseline? Say this is my baseline calculation. That's probably confusing. Let's say this is a special value x. So it's still x overall. No, is x that? I guess the power changes here. N minus 1, n minus 2. Yeah, it's not the same. Okay, so 99. So let's say this is equal to function x, or f of m, so f of, no, just ends up being exponential. So say function f of base power is base times base minus 1 to the power minus 1. So this is f of m, actually say to the power p, m 99. So here this is going to start with f of m and 98. You have a bunch of singletons and then a pair. F of n98 is always going to be, or f of something is always going to be the starting. And the pair appears. And here the pair can occur in 1 out of 98 ways. Right? Or is it 99? Actually, I think it's 99. So maybe this one's like 100 choose 0. Out of 100 things, choose 0 different things. Out of 99 things, choose 1 for the pairing. Here, base is going to be f n97 times, so you have 2 pairs now, and there's 98 spots. Right, there's 96 singletons, 2 pairs, so there's 98 things. You just choose 2. You choose 2. Or then this is going to be summed with, you choose 1 for 98. You choose 2 for, choose 2 for so you can have 2 pairs or you can have a triple. And for the triple, it would be 97 choose 1. 97 choose 1. Is that right? You have a triple and 97 singletons. No, that still ends up being 98. 98 things, triple which counts for 3 things. And then 97 things are singletons. How do these iteratively compare? So if we do f of 99 versus f of 98, then you're dividing by n minus 1. So going from k to k plus 1, you need to divide by a factor. You need to divide out a factor n minus 1. And then how the combinations things compare. How do the combinations thing compare? So going from 99, 100 choose 0, 99 choose 1. And then the 99 choose 1 becomes 98 choose 2. So you're replacing two singletons with one pair, so that goes down 1 here and up 1 here. Or you're replacing a pair and a singleton with a triplet. So if this is like, no, it's just bad. So choose 1 for your pair. This is choose 2 for your pairs. Choose 1 for your triple. Always 98, right? It's always 98. Things. Equals 100, k equals 3, 96. Here it'd be 97. So if this thing is 98, choose 2 pairs. You could trade that off with pair and triple. No, you can trade off with the triple and triple. Huh. You can trade off. Well, you're increasing your pair, so baseline is going to be 3 pairs. Choose 3 pairs. And then you can trade off a pair for triple. So it would be 2 pairs remaining and a triple. So it'd be like 97, choose 2 pair, and then, no, actually, can't, well, actually, yeah, you can't have 2 pairs. It has to go down to 1 pair. 2 pairs becomes a triple and a singleton. So you have 1 pair left over, and then it would be 96, choose 96, choose So there's 94, 95, 95 singletons. Or you can also do one triple. So I don't know if that's correct. 3 pairs becomes 3 pairs becomes a triple pair and a singleton. This ends up needing to be 97, choose 1, 96, choose 1, 97, choose 1, 96, choose 1. So this was originally 7, choose 5. Okay, what was it before 7? It was 6, choose. I think this was originally 6, right? No, when did I change this? Oof. Okay. So 10, 7, choose 5. Or I guess I can do 7, choose 1p. And then that gives me 6 remaining. I'm choosing 1t. Maybe I should be consistent, always choose like singletons first. Yeah, maybe I should be choosing singletons first, I don't know. So 99, choose 97 singletons. Well, is that right? 99. 99 spots. No, actually that's right. Maybe 90, 90, 99, choose 98 singleton spots. And then 97, choose 94 to be singletons. So 97, choose 94 singletons, which leaves 3 left over. No, okay, this is the original one. So this is the replacement for that thing. And the replacement for the second one was 97, choose 95 singletons. 95 singletons and 1 pair. This is like, there's 1 spot. There's 3 spots. There's 3 spots remaining, and I'm choosing 3 pairs. So 97, I'm choosing 95 spots to be singletons, and then of the 2 spots remaining, I'm choosing one of them to be a pair, and then of 1 spot remaining, I'm choosing one of them to be a triple. Okay. Can I relate it to k equals 2 or k equals 1? Two pairs to be a triple and a singleton. just what if it's something like the Fibonacci deal? No. Cannot do something that is n squared. It has to be linear. So 90, 100, choose 1. 100, choose 2. 100, choose 1. Or n is 100, k is 1. N is 100, k is 2. 2 pairs. N is 100, k is 1. The number of ways you take the number of ways where you get 97, choose 3. 97, choose 3. Each of those ways you should be able to uh, 97, choose 3. Maybe it's not relating k to k minus 1 or k minus 2, but it's sub-k'ing like I equals 0 to k. I equals 0 to k. '97, choose the number of singletons you have. Choose the number of singletons you have. The number of ways you can have some number of singletons. So it doesn't seem right. The number of ways you can have certain number of singletons. So you can have singletons if you had all pairs, then you'd have 94 singletons. No. If you had 3 pairs, then you'd have 97 singletons. That's not right either, is it? 97, choose 3 is the same thing as 97, choose 94. So you can have up to 94 singletons. It's always 97, choose your starting thing. So start by doing 97, choose your number singletons, which is 94. Alternatively, it could be 95 singletons. 97, choose 94, 97, choose 95. Alright. Oh my lord. Well, at least this one doesn't seem as bad as the last one that I never solved. That one still is trauma-inducing. I mean, it seems like there should be. Should I look at a hint? Seems like there should be a way. 97, choose 3. 97, choose. 97, choose 3. I should probably start with counting the singletons because the singletons are almost always there. Like you're not always sure if there's going to be a pair. You're not always sure if there's going to be a triple. Well, you're almost always sure there's going to be a singleton. I guess maybe I can look at the other way around. Like you can start with the maximum number of consecutive elements as your kind of single block. So if k is 1, then your single block is going to be a pair. If k is 2, then your single block is going to be a triple. If k is 3, then your single block is going to be a quadruple. And then you kind of break it up from there, maybe. So you think about how they break up a quadruple. And a quadruple can be broken up into a triple and a singleton. And then you go from how I break up the triple, and that can be broken up to a pair and a singleton. So you start off with thinking about your biggest block. So maybe if k is 3, your biggest block is a quadruple. And quadruple will take up 4. So if that's a quadruple block, that'd be 4, the 4 block, and then you have 96 singletons, so that's 97. 97 total blocks. And you're picking 1 for your quadruple. And then that breaks up into the quadruple can become triples. And somehow there should be 2 triples there. Does it always work with being 2? I guess it has to be, right? If it's like let's say an 8 block case, K7, there's this is K is 8, so there's this, K is 8, so there's this, K is 9, K is 7. 7 pairs, so it has to be 8 in a row. So yeah, there's an 8 block, and then if you break up the 8 block, it would be 2 ways of doing a 7 block. Yeah, so how many ways can you for each 8? Okay, so is that right? So Q, there's going to be 96 singletons, or the 96 singletons, or alright, this is too big. Let's say it's quadruple and 2 singletons. So there's 6 things. So is that 6 things? This looks like it's 3 things. So what is n here? So this n is 6. No, n is 7. Oh, n is 6. K is 3. So so this would be 3 choose 1. So quadruple, singleton, singleton, quadruple, singleton, single, quadruple. And then the quadruple can become a triple and a singleton. So like that could be how you break up the quadruple here. And then if you break up this quadruple, it's going to overlap. Like it's going to be STS and then SSTS. But this is not distinguishable from this. So it's not like every single one of these is going to branch off into something that is unique. Oof. What if you had okay, so what is this? This is going to be NCR 4 choose 1 triple. Your number of blocks increases by 1 because you trade off a quadruple for a singleton and a triple, so there's 4 blocks. And there's 1 triple that you get. And then you can trade off. Technically, you can go from this thing to 2 pairs. Right. You can trade off 1 quadruple for. What if you didn't try to do that? No, you kind of have to do that. Quadruple could become 2 pairs. Is that right? Each triple becomes 2 pairs. So it could become, or each triple in a singleton becomes 2 pairs. So therefore, you can get 2 pairs from this. then you can rearrange the two pairs. So it'd be something like 5, choose 2. What happened to the... Can you not have like a triple in a pair? Two pairs. Wait, is that right? That's not right, is it? Quadruple becomes a triple and a singleton. And then triple and a singleton can become two pairs. So if you have... No, you need to get to 3 pairs. What's going on here? K equals 3. This case 4. So you have 3 pairs. Yeah, you should have 3 pairs. One triple becomes 2 pairs. You have 3 pairs, pair and a triple. A pair and a triple. Oh no, okay. I forgot the rule. It's actually a quadruple and a quadruple and a singleton becomes a triple and a pair. Okay. Yeah, this is too simplified. Something like that. Quadruple becomes a triple and a pair. Oh, gee. So it'd be like 4 choose 1, 3 choose 1, and then 2 choose 2. Or is it actually? Is it just actually? Because there's actually only triple is 3, pair is 2, so that's 6. Or 5 plus 1 is 6. Yeah. Okay, so some combination of STP, right? And then the last thing is 3 choose 1, 2 choose 1. And you have a pair and a triple. You have another triple and a singleton, so you can replace it with... Oh no, you have triple, so quadruple and a singleton becomes a triple pair. And triple and a singleton becomes 2 pairs. So it's 3 choose 1. Actually, 3 choose 0. Three choose 0. So you start off with your biggest block. You can break your biggest block into a pair and your second biggest block. Quadruple becomes a pair and a triple. If it's a quintuple, 5 in a row, then it becomes quadruple and a pair. Okay, so maybe these letters were worse. So if it's 5 in a row, then it becomes 4 and 2. Yeah, and then if it's 4 in a row, then it becomes 3 and 2. So it can become 3, 2, 2. And if it's 3 in a row, wait, how is this working? 3 in a row, it should be able to become it needs a singleton, right? So this is currently 7, 8. So if it's 3 in a row, it can become 2 pairs. 3 in a row and a singleton becomes 2 pairs. Did I miss anything? 5 in a row. 5 in a row. 5 in a row and a singleton becomes 4 in a row and a pair. And then 4 in a row and a singleton becomes 3 in a row and another pair. 5, 1 becomes 4, 2. 4, 2 becomes, 4, 1 becomes 3, 2. 3 and 1 becomes 2 and 2. Interesting. Five and 1, 4 and 2. 4 and 1, 3 and 2. I wish I was better at math. Three and 1 becomes 2 and 2. Is there a way for me to make that to some form of relation? 5, 1, 4, 2. 4, 1, 3. 4, 1, 3, 2. And then you have to consider how many ways to reorder that as well. I wonder, why does it seem like, what was the one before here? The one before here was like 4, 1, 1 becomes 3, 2, and then 3, 1 becomes 2. So if it was like 6, 1, 1, 1, it's kind of 9, 10, and it becomes 5, 2, and the 5, 2 becomes 4, 2, and then the 4, 2 becomes 3, 4, 1 becomes 3, 2, and the 3, 2 becomes, the 3, 1 becomes 2. there should be a way to get two threes in here. Should be a way to get 2 3s in here, I think. A three in a row has 4 things in it. 3 in a row, no. 3 in a row is the same thing as 4 pairs. Maybe I can't. Maybe these numbers are still too small. 6 in a row, it says 5 things. Okay, so a little more. 7 1 1 1 1. It's 11 12. 7 6 2. 6 1 becomes 5 2. 5 1 becomes 4 2. 4 1 becomes 3 2. 3 1 becomes 2 2. So 7 has 8 things in it. Seven should be able to break into like a 3 and a 3. Seven breaks into 6 2. Why isn't there one where it has 2 3s in it? 7 in a row. That's equivalent to, each 7 is equivalent to, well, 7 in a row means there's 8 numbers. So this is k equals 6. K equals 6. So you have 7 in a row. Equals 6. Here n is equal to 12. Can't we have some triples here? Like 2 triples? Each triple represents 3 things in a row. The triple represents 3 things in a row. So triple and 1. No, triple and 2 replaces the 4 and 1. Triple and 2 replaces the 4 and 1. So I mean, there's 2 2 2 here, so it should be like 4 1 1 2 2 2. So there should be something that's like 4 1 1 4 4 4 1 1 1. Right. Should be something like that. So where is it supposed to show up? 7 1 6 2. And 6 1 becomes 2. 7 1 should become 4 4 as well. 7 1 becomes 4 4. So I think should have had 5 1 becomes 5 1 becomes 3, 1, 3, 1. So 5, 5, 1 becomes 3, 3. 5, 1 becomes 4, 2, or 3, 3. Okay. 5, 1 becomes 4, 2, or 3, 3. So 6, 1 becomes 5, 2. It could also become 4, 3. Right? 4, 3. So 6 in a row. That's when k is equal to, this is k equals 3. This is k equals 4. This is k equals 5. 6 in a row. So if you had a 4 in a row, then that takes is equivalent to 3 pairs. And then 2 in a row is equivalent to, or 3 in a row is equivalent to another 2 pairs. And then 3 plus 2 is 5. So for each number, for each big number in 1, it breaks off into every combination of every way that you can divide that big number in 1 to a smaller number. So 6, 1 becomes 4, 3, or 5, 2. And then 5, 2. Wait. This looks like every single possible way of allocating some number n into some number of buckets, where each bucket needs at least 1. I guess each way of allocation here is not necessarily one way. It needs to be calculated individually, maybe. It is somewhat interesting. So here n is 6, k is 3, so it's like 4, 1, 1, which is this thing. Or it could be 3, 2, 1, which is that. Or it could be 2, 2, 2, which is the 3 triples. Interesting. Hmm. 4, 1, 1, 3, 2, 1, 2, 2, 2. How many ways can you rearrange 4, 1, 1? How many ways can you rearrange 4, 1, 1? How many ways can you rearrange 3, 2, 1? How many ways can you rearrange 2, 2, 2? I guess you need to know how many duplicates you have. Interesting. Interesting. Let me rearrange 411 is n factorial over 2 factorial, where n is the number of things here. So this is 3 factorial divided by 2 factorial because there's 2 ones. So that's 6 over 2, so that's 3. And this is 3 things divided by 1 factorial, 1 factorial, 1 factorial. So that's 3 things. And this is 3 factorial divided by 2 factorial. No, 2 is repeated 3 times, so it's 3 factorial. So that's 1. Interesting. Huh. 411 321 222. They do like a count of the frequency that certain numbers appear. You do n factorial. N is like the number of objects factorial. So it's not really, you don't need combinations to calculate it. Probably shouldn't use combinations given how this is presented. Okay, so there's like 611 becomes 52. It's not necessarily the most straightforward. 6111. And then, yeah, K is like, K can be huge. K can be 10,000. So having 10,000 10,000 rows in this, 10,000 rows in this is where each row needs a separate formula to calculate the frequencies. Great. Alright, but let's see if I can do something here. 6 4 ones, 5 2. So I'm replacing a 6 and a 1 with 5 and a 2. And then I'm replacing the 6 and 1 with 4 and 3. Or, I guess those are the only 2. Six and a 1. 6 and a 1 with 5. 6 and a 1. I reduce the number of 1s. Reduce the number of 6s. Increase the number of 5s. Increase the number of 2s. I reduce the number of 5s, the number of 2s. Increase the number of 4s and 3s. I can never reduce 1s to 0s. Well, I can actually. Reduce 5 and 1. I get 4 and 2. 6, 1, 1, 1, 1, 1. So if you start off with, say, n is 100 and k is 50. So you start with 50 and a bunch of ones. No, sorry, you start with 51 consecutive. So k is 49. So you start with 50 consecutive. What should k be? Let's say k is 50. Sure. Start with 51 and a bunch of ones. Then you go 52 and 50 and 2, or 49 and 3, or 47 and 48 and 4. All the way down to 25 and 25. I guess it's 26 and 26. And then what? And then you need to break up those secondary numbers, possibly. So, for instance, the 49, 3, 1, that could be 49, 2, 2. Right, so 4, 4, 3, 1 can break down to 4, 3, 1 here becomes 2, 2. I guess. Yeah. And then the 48, 4, 1 could be 48, 3, 2. Yeah, and then the 48, 3, 2 becomes 48, 3, 2, 2. Alright, so 50 and 1, 50 and 2, 49, 3, 3, 1 becomes a 2, 2. And then 48, 4, 1, 48, 4, 4, 1 becomes 3, 2. And then the 3, 1 becomes a, no, oops, this should be 2, 2. Oh, wait. What do we have here? 4, 1, 1 here is 4, 1, 1, 3, 2, 1, 2, 2, 2. And that was one of the previous solutions. That was k equals 3. That was k equals 3. Interesting. Forty-eight, 4, 1, 1, 1 becomes 48, 3, 2, 1. 48, 2, 2, 2. Is that somehow calculatable? Or even 51, 51 and 1 becomes 26, 26. 4, 1, 1. Wonder why. Well, the 4, 1 here does become, if I ignore the 2, 4, 1 here becomes 3, 2, and 3, 2 becomes 2, 2, 2. So the 2 here has the same thing in it, just rearranged maybe. I kept my pairs at the end. I kept my pairs at the end. 4, 1 becomes 3, 1. 3, 1 becomes 2. No, doesn't make sense. This 4 and this 1 becomes this 3 and this 2. This 3 and this 1 becomes just these 2's. 5, 1 becomes 4, 2. 4, 1 becomes 3, 2. 5, 1 becomes 4, 2, but 5, 1 can also become 5, becomes 3, 3. I always take the 1s from the ends. They always get replaced by something that is bigger. Hmm. One, 4, 2. 5, 1 becomes 4, 2, but because there's still because that 4 has another 1 in it, I can use k equals 3 maybe? Is this the k equals 3 process? Is the k equals 3 process? Okay, yeah. Has to be one pass. K equals 4. We have 5, 1. We have 5, 1. Yeah, so if your frequency if you do for each level here, this cannot take the frequency of each of these counts. Just is too slow. We'd be for every level from I to K, from 0 to K. You'd be counting the number of each thing. This is too slow. Four, 1, 1. 4, 1, 1. 4, 1 becomes 3, 2. And then the 3, 1 becomes 2, 2. 3, 1 becomes a 2, 2. 4, 1 becomes a 3, 2. But the 4 can also become a 2, 2. No. The 4, 1 can become 3, 2. 4, 1 becomes 3, 2. 3, 1 becomes 3, 1 becomes 2, 2, 2, 2, 2. N equals 6. N equals 6. K equals 3. K equals 3. So N equals 3, K equals 1. That's your starting point. N equals 3, K equals 1. N equals 6. 6 elements. K equals 3. 3 pairs. So 1 block of 4, 2 singletons. Or 0 singletons, K pairs. Singletons will be N minus 2K singletons. What is the N equals 6? K could equal 0, 1, or 0, 1, 2, or 3. N equals 6, K could equal 0, 1, 2, or 3. 0 is straightforward. N equals 6. Equals 0, 1, 2, 3. So it equals 1. So be that K equals 2 would be like that. Or like that. And K equals 3 would be like that, or that. Can't have k equals 4 because that's too little. So, is there any relationship between k equals 1 to k equals, or k equals 0 to k equals 3? You have all singletons. You don't have any pairs. And then you have 4 singletons in a pair. And then you have 2 singletons in 2 pairs, or 3 singletons in a triple. So you're placing 2. You're replacing 2 ones with a 2. Yeah, you're placing 2 ones with a 2 and a 0, I guess. Yeah, 2 ones with a 2 and 0. Right. So the 2 ones, the 2 ones here became a 2 and a 0. So it all empties out to 6 elements, some of which are zeros. Of course, the zeros don't really count. Huh. So it'd be 6 choose 0. You have 6 choose 0, and then 6 choose 1. Then 4 1 1 0 0 0 is the same thing as 0 0 0 4 1 1. So we're not really choosing your zeros. K equals 1, 2, or 3. You have if you have 2 1 1, how does that relate? Yeah, I don't know if these zeros have any bearing on anything. K equals 0 of all ones. K equals 1. You have a 2 in all ones. K equals 2. You have 3 and all 1s. It is 3, you have 4 and all 1s. 4, 3, 2. 2 becomes, what's 3, 1 becomes 2, 2. Number of ways you can rearrange it. Exactly k indices satisfy the condition. Each element of the array is inclusive. Exactly k indices satisfy the condition. You just do n choose k minus 1. N minus 1 choose k minus 1. And if not, then why not? N minus 1 choose k minus 1. So out of the n minus 1 elements that are differing from the previous element, or n minus 1 element that has a previous element, choose k minus, choose k of them to be the same. N minus 1 choose k. I guess if you have n minus 1 choose k, no, that can't possibly be that. Like it would just be exactly k indices. N minus 1 choose k. And the other indices would be differing from the previous one. So if you have n minus 1 choose k, then each of those spots has only one way of doing it. And then you have minus 1 choose k. Sure. Say k is, say n is 6, k is 3, and m is 4. Let's do something small. N is 6, k is 3, m is 4, sure. So what is the answer to this? N is 6, m is 4, k is 3. That's gonna crash. 360. So could you do something straightforward like say out of the n-1 spots? So you have k equals 3. So 3 has to be the same. So let's say it needs to be one of these spots. So out of those spots, there has to be, you pick 3 of them. So 5, choose 3. And then that means that the other spots, well, there's 4 ways of doing this one. And if you pick 3 spots, those 3 spots will only have one way of doing those. So like they're going to be 1, 1, 1. And then the remaining spots, they have to be different. So it has to be 3 and 3 here. So it's like 5, choose 3 to be the same as the previous ones. Oh, what is 5, choose 3? Right? 4, 1, 3, 1, 1. Five, choose 3. 10. 10 times 4 times 3 times 3. 10 times 3, 6. So the value is the same. It's this thing. And then it's math.combinations n-1, choose k, comes the value. Let's comment out this. Let's try a harder test case. Probably need mod here. Oh my god. Oh my god. That's so stupid. I'm so my god. Holy cow. I made this way too hard. I made this way too hard. Alright, I think this is actually just the general formula. we just need to I need to optimize math.com. Math.combinations. Okay. So optimize math.combinations. For faster combination calculation, Python. Can you use mod in this math combinations? Pre-compute factorials and inverse factorials. Using math is the most straightforward. What is this? Compute the commutative sum of those logs. Okay. Optimizations. Reduce factorial calculations when calculating NCR is more efficient to reduce the number of factorial operations. Calculating a full factorial, use the following. N factorial. Interesting. So K can be, so N choose R, N minus 1K is the same thing as N minus 1 choose N minus K minus 1. I guess I can test whether or not that's actually better. Times the value modded. I don't think this is any faster. I mean, K could be whatever the larger or the smaller is. For multiple calculations with the same n, pre-computing factorials. Pre-compute factorials. New tools, functions generate combinations on demand, avoid the need to store all combinations in memory at once. This can be many efficient, especially when dealing with large input sets. Note that this does not calculate the number of combinations, but rather generates combinations. What is the faster way of calculating combinations here? M times power of m minus 1 to the power of n minus k mod. And then you mod that. Math.combinations n minus k minus reduce factorial calculations. You calculate combinations for different values of k, but the same value pre-compute. Dealing problems with third-party combinations repeatedly, look into using dynamic programs, which is for simple calculations, use MS. If you need to generate combinations for performance, use modular arithmetic, pre-computed and inverse factorials. You're dealing with large number combinations used today. Here's a single combination calculation here. So I don't know if pre-computing the factorials is going to help. For every combination, and choose R, and choose R. So why is this? I mean, I assume this has to be pretty damn fast. It's the power with the modulo. What would make the math combination thing faster? I guess maybe you don't have to do mod here if you're going to actually do the mod in the next step. And maybe you don't even have that value, you can just say this thing times this thing. I don't think that helps at all though. I guess it's one less modulo calculation. Huh. Man, there's some super fast runtimes here. I wonder, math.combinations, n-1 spots, you're choosing k spots to have your repeat values at. So let's see here. NCR n-1k is equal to n-1 factorial divided by k factorial and n-1 minus k factorial. So you could possibly do n-1. What was the thing? It's like n-1 times, it's n-1 times, okay, say the p is equal to n-1, and for every spot in the range of k, it's going to be p times equals, let's say the product is equal to 1, and the factor is equal to n-1, then you say product times equals the factor, and then you decrement the factor, and then you return the product times the value modded. That's the other kind of way of calculating combinations, I believe. Just did it wrong. K is 0. Does it work for k is 1? And works for k is 0, doesn't work for k is 2. So it's n-1 factorial. If you divide out the k factorial from it, then it's n-1 down to, you should have k terms within it, and it should be reducing by 1 each time, I think. n-1 choose n minus 1 choose n minus 1 choose k. I wonder if you need, no, I don't think you need to have %mod here. Okay, let me double check here. Let's say the product is 1, and let's say you're choosing 5, choose 3. So the factor is starting with 5, for I in the range of 3. Product times equals product, and product times equals the factor decrements, and then print out what the product is. 5 choose 3. 5 choose 3 is not 60. Should this be 5 choose 3? Should be 5 times 4 times the number of things is what you're choosing. 5 times 4 times 3. Am I confusing with this with permutations? 5 permute 2. Yeah, I'm confusing with permutations. It should be 5. It should be divided by 3 times 2 times 1. Yeah. Now I guess the question is there's a factorial calculation. So it's good. This should be the numerator, and then there should be a denominator. So the numerator should be starting with 1. Denominator should start with 1. Let's say 1 to k plus 1. The numerator times equals the factor, and the denominator times equals I, and you get the numerator divided by denominator times value modded. Okay. Is this any faster than doing math.combination? Probably not. In fact, it is significantly slower. Fuck. Time limit exceeded. Yeah, that's just not gonna work. I guess I'm actually kind of concerned why this exceeds the time limit. Is this because of the large numbers? Factor times numerator odd. Mod. I could even, yeah, whatever. How to optimize, oh lord. Output is 0. That's interesting. The numerator. Okay, this is clearly not it. This is clearly not it. So math combinations n minus 1k was the original thing times value. Oh. Alright, come on. Okay, back to the correct answer. Back to the slow runtime. Faster combination calculation modulo. Optimized library. And I wonder if I did this modulo exponentiation. Using the multiplicative formula to compute the next tier, the next number from the previous, but with keeping the number small. Numbers of combinations modulo m efficient. And choose m. Okay, let's go ahead and use the excellent technology that is copy paste. Okay. Say what's going on here? Define n. Okay, so nm is just. The hell is this? Nm is the mapping to integers of this stuff. Okay, sure. So nm, is that the same thing as n choose m? For everything in the range of C. No, it's m choose n. M choose n. Looks like. Maybe. N and m are m is the modular number. How do you pick what you're choosing? What the hell? K in the range of n, you would see you're choosing 1. K in range n. Multiplication is finer modulo if for only c times n minus k. So instead of dividing k plus 1, we divide by inverse k plus 1 modulo m. I see. Not all numbers have an inverse modulo. You can multiply the numbers 6 rough times. So and choose I in the range of that. I just want to get a fast combination modulo arithmetic deal. Modular exponentiation in Python. I don't think you need this, right? I already looked at this at some point. Interesting. And choose R. If R is greater than n, return 1, return 0. Otherwise, return this thing plus this thing. This is a very naive approach. Okay. Using factorial O of n time O of 1 space. Using avoiding factorial combination. I feel like I've done this before. Avoiding factorial computations. Multiplier. Expected approach by using binomial coefficient formula O of R time O of 1 space. Calculate the value of n, choose R using binomial coefficient. Logarithmic O of R time was R. R is what you choose, okay, and choose R, I think. Logarithmic approach using O of R time O of 1 space. Logarithmic formula. Okay. Okay. Let's go. I'm so done right now. Let's go. What is this? I don't know. Math combinations. I don't even know if this is going to work for big numbers. I assume it's using mathlog, so maybe it's probably fast enough. NCR. Has to be good enough, right? Okay. Math error range. Mod, help. Actually, this probably needs to be. So this thing doesn't RES is probably too big. Wait, this is, oh shit. This is logarithmic. I can't just use modulo, I don't think. Math exponential to resource round. I wonder if round can be mod. I see. I think maybe I should do math exponential, take the mod of that, and then round it. Maybe? Ugh, not quite. So math exponential to the result. So it's 10 to the 10th power. That's really big. Calculate the logarithmic sum of the numerator and denominator using the loop. Logarithmic sum of the numerator and denominator using the loop. So you're taking the log of a big, taking log of the product. Taking log of the number of combinations. So therefore you're subtract, you take the log of a quotient. It's going to be adding the log of the factor in the numerator, subtracting log of the factor in the denominator. And then you give that to your result. I think you can possibly, can you do the log? Can you do that under modulo? It's all under modulo. Okay, this is too complicated. Non-logarithmic approach. Too complicated. Okay, let's see if that works. Does it work for the big one? It does. Okay. Oh no, it seems too slow. Seems too slow. Yeah, okay. Time limits. You failed me, geeks for geeks. Failed me. Of n time of one space. Okay, so all right, let's try your other approach here. What you can do? All right, whatever. For the love of God. Please let this be fast enough. Alright, this is the last thing. If it's not fast enough, it's not fast enough. It's not fast enough. Alright, let's see. Math.combinations. Literally 3 lines of code, and then more than 3 hours later, and more than 3,000 milliseconds later, I'm going to accept the results. Accept the results. Okay. Summary. Well, don't overthink it. The most straightforward maybe idea to arrive at a way to calculate would be if there are exactly k indices where the value matches the previous value at that index matches the previous, then out of n-1 indices that have a previous value, which is again basically everything after index 0. Choose k of them to use the same value. The other indices must have a different value than the previous. So for any, so this basically implies that you use NCR n-1, choose k. And then for that's part A. Part B is for each way that is chosen, for each combination there, how many ways to fill in the indices. So basically, let's take an example. If it was like 10, n is 10, k is 3, i.e. there's going to be 10 spots. 10 spots. 0, 1, 2. I'll use indices for the spots here. So if there's going to be 3, then let's say, you know, this is one of the spots. This is another spot. This is another spot. The number of ways of doing those spots would just be 1. Of doing spots that have doing k spots that are chosen is 1, same as prior value. And then the number of ways of doing the first spot is always number of ways of doing first spot is equal to m, since anything is available, since all values are okay. And then number of ways of doing each other spot is equal to 3, or m minus 1, 1 less, since it can't match previous. So here it'd be like 3, 3, 3, 3, 3, 3. So overall, that's going to be m times m minus 1 times to the power of however many 3 spots there are, or n minus 1 spots there are, which is n minus k minus 1. So overall, it's number of ways to pick spots to repeat times number of ways to fill spots with values. And overall, that's going to be ncr n minus 1k times this thing. I'll call this x. And then, if you can find a better way to do that calculation, good job. Time complexity, this is O of how fast is combination calculations? O of n or combination calculation? I'm actually not sure. This seems pretty darn slow. It might be O of n factorial. The O. No, n factorial is just that's ridiculous. This one I'm really not sure. It's whatever O of like math.combinations of n takes, and the space complexity is O of 1.